A balanced scale with equal weights on each side, a stalemate during a tug of war, and an equal amount of supply and demand are all examples of a type of equilibrium, a kind of state of balance that's achieved due to opposing forces. Chemistry is subject to a notion of equilibrium as well, and we're going to go over it right now. Imagine a simple chemical reaction with species A and B, denoted as shown on the screen. The double arrow that's in the middle of A and B means that the reaction is going both ways. That is to say, the reactants are turning into the product species, while products are turning back into the reactant species. Suppose that the A molecules start turning into the B molecules whenever the temperature rises above room temperature. Inasmuch, imagine placing a test tube with only A molecules into an oven that maintains a constant temperature above room temperature. Given what I just mentioned, you would expect that some A molecules will start turning into B molecules. As time passes, more and more A molecules will turn into B molecules. However, suppose that there is also a backward tendency for B molecules to turn into A molecules for a large range of temperatures, including the one in the oven. What will result is a back and forth movement between the concentrations of products and reactants, with the possibility of a chemical equilibrium eventually being established. A chemical equilibrium is a state in which the rate of the forward reaction is the same as the rate of the reverse reaction. In our example, this means that after a certain period of time, the concentrations of species A and B will reach a stable state in which just as many A molecules will be turning into B molecules as B molecules turning into A molecules. In other words, the reaction will reach equilibrium, which could be maintained indefinitely if all factors, such as temperature, remain the same. Knowing this, you can now understand the next part of equilibrium as it relates to chemistry.
Well, Kc is the equilibrium constant, and it involves the concentration of the reactants and products at equilibrium. The clue is in the name. Whereas Q is the reaction quotient, and that involves the concentration of reactants and products when they're not at equilibrium. Unfortunately, the clue isn't in that name. So let's look at a graph of the Haber process as it approaches equilibrium. You can see that there are three lines there corresponding to the three reactants and products. The concentration of hydrogen is decreasing as the reaction proceeds, as is the concentration of nitrogen. But the concentration of ammonia is increasing, all of them on their way to equilibrium. Let me write out the Kc expression for the reaction, and it looks like at 40 seconds the concentrations are unchanging, and so we are at equilibrium. Now it looks like the rate of reaction is also zero, because the gradient of the curve at that point is zero. The gradient being the change of concentration over the change in time. But don't forget, the reaction hasn't finished. We're at dynamic equilibrium. It's continuing. Let's put in the numbers at time 40, which is when equilibrium begins. And that will give me Kc, the equilibrium constant. Now for clarity, I'm ignoring the units. The units video comes up later. Okay, so that's my value of Kc. Now what about at 10 seconds? Now we can't work out Kc at 10 seconds. Kc only applies when we're at equilibrium. So we're going to use Q, the reaction quotient, because we're not at equilibrium. Putting in the numbers. Well, that's good. I didn't want the same value as Kc. Something would have gone wrong otherwise. Now I'm going to work out the values for Q at t equals 20 and 30 seconds off board and summarize them in a table. Now notice that Q is always going to approach Kc. But of course, when Q equals Kc, you're at equilibrium. And I suppose Q no longer makes any sense. Now in our case, as the reaction proceeds, there's more and more ammonia being produced, more and more product being produced. And you can see from looking at the table that if Q is smaller than Kc, which is the case here, then the reaction must be proceeding to the right before it reaches equilibrium. And conversely, if Q is greater than Kc, then the reaction is proceeding to the left until it reaches equilibrium.
Okay, the extent of the reaction and the magnitude of the equilibrium constant Kc. This is the Haber process, you should know this by now. And Kc is the products raised to the power of the coefficient divided by the reactants raised to the power of their coefficients. And let's say Kc in this case is, I don't know, 1,000. So 1,000's a big number, and bigger than 1 is how it's put in the syllabus. So that means there's lots of ammonia. So essentially the products are heavily favoured. Lots and lots of products at equilibrium, hardly any reactants. And so to quote the syllabus, almost to completion. Well, I'm not sure what that means. It's equilibrium, it never reaches completion, but that's in the syllabus. Alrighty, now let's look at the opposite. Let's say that my Kc is 1 over 1,000, so that means that there's loads and loads of reactants, less than 1. So the reactants are favoured in this case, and the reaction hardly proceeds. Now, don't think that that means that the forward and reverse reaction rates are different. No, it's equilibrium. The forward and reversed reaction rates are the same. Don't fall for that trap.